mute until the training is, let's say, somewhere in the break point. Then I will give you a minute to ask questions. It's better to ask questions in the text in the chat. I can see it. I can see it in my menu when there will be new question. So anytime you can text there. First
Hello.
of all,
Good morning, sir. This time I would request you to enable the chat, please, for our questions.
Yeah, it's enabled. I wasn't able to see it, but now I can see it.
Oh, thank you.
I see that last time there was questions about tip angle. What is the best tip angle of the drill? But it's a very unspecific question, so I responded to every question except this one. When you ask question, it has to be really specific.
With the minimum effort, I had read that question to what should be the angle to drill a hole with minimum effort. That was the question from one of my colleagues.
But that doesn't depend. It doesn't depend on the drill angle. Yeah, it depends on the grinding of the split point, on the geometry of the drill, also on the flute angle. So
also you share the link for the catalog. I could not open it, so if you could give this link, it will be nice. It will be grateful.
That's the reason why I in the end of the training, I highlighted some products that are specific for each material group. So basically, when it's good for some material group, then it of course will have less thrust force because the geometry is specific for the material.
Okay.
I see. Okay, let's go to the training.
Okay.
So first, for all our team members, I will show where you can find the material that I will train now. You can find the material for grades overview and tube breakers overview here in files in cross tables. So I will use this material for the presentation because it's very easy to find. I'm sorry. Excuse me. It's easy to find in the Teams, but of course you can find this material also on websites in a category of posters. So first, let's take a look at the grades of Pramet that we currently have. This poster is from 2017. Now we work on a new redesign for 2020. There already has been development of grades, so I will highlight which products are new, which are already replaced. There will be some mentions. So for the turning grades, basically we have two main groups: CVD grades, which are here in the beginning, starting with numbers T9, T7, and T5. Also older grades 66. And then we have second group of PVD grades, It starts with numbers T6, T8, and also T0, the specific grade for non-ferrous, aluminium, and copper alloys. Then we also have uncoated grades, these two, HF7 and H7, Pramet, and very specific HSS coated grade for broaching, which we will not focus on today. Let's focus on more on turning. Basically, for most of turning applications, it's recommended to use CVD grades just because they have a higher tool life in general than PVD grades. But it very depends on conditions, how we use it and where we use it. So for general turning of general materials like steel, some stainless steels and some cast irons, there are the grades T9. Then the next number 3 tells us about information about the family of the grades. Let's say what generation of the grade it is. Before there was T92, and in the future, maybe next year already, there will be grade T94, next generation. So this number is not so important for you. What is important for you to know is the last number, which represents basically hardness of the grade and the wear resistance. So if the number is small, it tells you that the grade is hard. Usually it have very thick coating and is very resistant. On the other hand, when the number in the end is high, like 35 or 45, it tells you that the grade is very tough. It can withstand lots of interruptions, and usually it has a very thin coating. It also represents here in the graphic section. It's represented here, so you can logically guess from the graph what the grade is and what is it good for. So there is good comparison in between, let's say, this hardest grade for steel turning and toughest grade for steel turning. So if we compare, okay, I'll make a snapshot so it's easier. So if we compare these two, this is the hardest grade. And this is the tough grade. So if we take a look here, what does it tell to us? First in the row of application, we can see black square. It means that the grade is really good for P1 up to P15 steels. That means it's very good for soft steel turning. And black square tells us it's good for the application. Half square, it tells us it's also a good option, but not the first choice. It means there will be better choice in the assortment, so it's better to look elsewhere. For cast irons, basically gray cast irons, ductile cast irons, it's good, but there will be better choice. And it can be also useful for hardened workpieces because the grade is hard and very resistant. The next column here tells us information about the feed rate. What feed rates can we use with this kind of grade? Here you can notice it has empty, the smallest triangle is empty. It means it's not really good to use a small feed rate with this kind of grades. Basically, for all FGM grades, that's all of these, and the old ones here, it's not good to use feed rate smaller than 0.15. So the feed rate should be always bigger than 0.15 in classical conditions. Of course, if you have small depth of cut and sharp geometry, if the load is not so big, you can have even smaller feed rate than 0.15, but it's not really recommended. That's because of the structure of the grade. There can be, let's say, premature chipping. So the chipping of the coating and of the substrate undercoating can be too soon. In information about cutting speed, it will tell you what kind of cutting speeds is favorable for this type of grade. So, for example, this hardest grade really likes to have high cutting speeds, so somewhere around maybe 300 up to 400. These hard grades, it's favorable. Because of the high cutting speed, it also have good productivity and a good heat on the cutting edge, so it can remove the material easily. Also, not so much sticking on the surface of thick coating. So high cutting speed is favorable here for hard grades. So high cutting speed. But on the other hand, when we move to more tough grades, like 25 or 35, then we need to go lower on cutting speeds. So basically, the cutting speed go like this. In next column, we can see resistance to adverse cutting condition. This represents how resistant is the grade to basically interruptions. And if we have, let's say, machine in a bad shape, in meaning there can be run out on the spindle, or there can be some other problem with maybe with feeding of the machine, or chip jamming inside in internal turning. So there will be more interruptions and vibrations to the insert itself. So this information tells us how resistant the grade is to these vibrations and interruptions. And we can see basically from hard grades aren't so tough, aren't so resistant to vibrations. So they don't like vibrations. But when we go with higher toughness, it can withstand even high vibrations and interruptions. The information to the right side of the column will tell us what kind of substrate it is. FGM, that's a very specific functional gradient material. That I will not explain this now in the beginner in the basic training. We can speak about it next week in let's say advanced training. And what kind of coating is MT-CVD? What kind of coating is PVD? Basically, good to remember that CVD is more wear resistant, more heat resistant, so it's better for productive turning, especially for if you have continuous cut and big chip loads. Then CVD usually is better. All the time, let's say, it's better. And let's jump back. Then we have mentioned here color of the insert. Actually, it's not completely black. It can be black grayish for the grade 53, it's black, brownish, almost like khaki color. But it's very close to black. We also have CVD, these older grades, these MT CVD grades, have top layer of titanium nitride coating, tin coating, that's gold color, and customers really like it, gold color on the top. Then we have here a column for coolant benefit. Actually, for all grades, it's better to have coolant, but then it depends what kind of cutting is it. If it's very short cutting with very short length, it can be even better to don't turn the cooling on, because the insert will have big thermal shocks. So in the beginning of the cutting, the insert is cool, it's cold. When it starts to cut, the temperature increase, and when it's stop cutting, it rapidly drops the temperature. So it can have thermal shocks. So for very short cutting, it's better. If it's just few millimeters, it can be better not turn cooling on. And for interrupted cutting, when it's heavily interrupted cut, it can be also better. Don't turn the cooling on. But in general, it's always better to use coolant for general applications. Then we have here 4 columns which tell us for what kind of application the grade is good for, or what kind of application it was developed for. We can see in some CVD grades we also use it for parting on the heavy roughing. So we can see the grade 9325 in parting, and newly also 7325. We can see it in GL family for parting inserts, and more tough grades are usually used for heavy roughing. But also 9315, it's very common for heavy roughing inserts, for big inserts like SCMT 3038. On the right side, there is very useful information about the grade, let's say the grade description. It's good to search for some keywords. So we can pick one of them. For example, here, one of the toughest grade, which is especially suitable for adverse cutting condition, medium to high feed rates, and medium cutting speeds. So it already tells us a lot of information that we need to know. So it's tough, suitable for adverse condition, so suitable for interruptions, vibrations, and with let's say high feed rates, medium cutting speeds. High feed rates and medium cutting speeds, this is very theoretical words, but it has to be, because it always depends on the size of the insert, size of the machine, and size of the workpiece. If we use really big insert like SCMT 38 that have big thickness, we can achieve depth of cut 15 millimeters and feed rate 0.9 or even 1.3 millimeters per revolution, but with cutting speeds 60 or 70 meters per minute. On the other hand, when we have smaller workpiece and smaller insert, then of course high feed rates can mean completely different number. So with CNMG 12, high feed rates represent somewhere around 0.5. This is already very high number, or 0.4 is a high number. And medium cutting speeds also depends on kind of workpiece. So we always need to consider what kind of workpiece we are doing and what size of insert. And then take a look, is it medium cutting speed or is it high feed rate? And then we have some additional information. Compared to its predecessors, that maybe you even don't know what predecessors it has. M15 and up to M40, it is not only tougher but more abrasion wear resistant, which will be useful when using intensive cutting conditions. So this doesn't tell you too much information, maybe just it can be used also for stainless steels, for tough stainless steels, that it has bigger wear resistance. So this information in the end can be very useful when you're not really sure what is the specific of the grade, what is it good for. So now when we take a look at the families, the rules applied are still the same. So the first number will tell you about the family of the grade. So, T9 are grades for steel turning in general. T7 are grades for stainless steels. That's the main focus. And also super alloys like nickel super alloys and cobalt super alloys. T5 is the main focus area of cast iron. So it's grade developed especially for cast iron with thick coating and with high wear resistance. You can see here it's not really resistant to vibrations or interruptions. So for interrupted cut, it's better to select different grade, like 9325 maybe, or some of the older grades like 6630 or even PVD grade when it's highly interrupted cut. And then we have this family 66, which are older grades, especially useful for old machines and bad setup on the machine. When we take a look at PVD grades, we can separate, we can divide these into two groups, basically. T6, which is material specific for especially good for special alloys, special nickel alloys or cobalt alloys, and it's also very good for stainless steel finishing or semi-finishing. It gives us really nice heat resistance, but in combination with sharpness of PVD grade, there is, say, one big difference between PVD and CVD, and that's that in general all PVD grades can withstand more interruption than CVD grades. So in general, PVD grades we use for interrupted cut or some specific conditions, and CVD grades we use for general conditions, because in continuous cut it provides us higher tool life. Also, good to mention, PVD grades are sharper than CVD grades. So especially this 6310 is the reason why we use it for finishing of stainless. And when we take a look at the family T8, it has lots of different grades, and each grade is specific for something else. So when we take a look at T8310, that's specific for finishing, and we cannot find it connected with too many inserts. It's quite rare, and it's very how to say, very hard but also brittle grade. On the other hand, T8315 is very popular grade for finishing of steel, stainless steels, also cast irons, and it's also very useful grade for interrupted cut of in cast irons and non-ferrous materials. We always have to consider how big is the chip load. If the chip is too big, use tougher grade. If it's small chip, this grade can be a really good choice. Then highlighted grade here, let's say the first choice from Pvd when we don't know what we're going to do, is T8330, which gives us nice balance between wear resistance, hardness, and also toughness of the grade. The only thing that we need to consider is to apply, let's say, low cutting speed, and then this grade works very nicely for any kind of material and any kind of condition. It's perfect choice for interrupted cut when we don't know the specific material or specific workpiece. It is quite thin PVD coating, and the grade is tough enough to withstand any kind of interruption. T8345, that's specific for heavy milling, heavy turning. That's very tough grade for the biggest chip loads, especially in stainless steels and superalloys. Then T8030 is there for threading, and T0, that's completely different family. That's specific grade for aluminum and let's say all non-ferrous or sticky materials. It's polished PVD coated grade. So I really recommend to download this file or see it in Teams. You can find it also in on websites, in download section, in posters. And what I find useful is the description of the grade. So for each grade, it will tell you some additional information and what the grade is really good for. So now let's move on to overview of chip breakers that we made for Cutting Days 2017, and it's still valid and still very useful file. You can find on the it's and try to explain how is it designed and what does it show to you. So we can see it's divided into 6 subgroups per ISO coding, so PM, K, and SH. And from left to right, we can see grades in the beginning. Then we can see negative or positive chip breakers here. So chip breakers on negative inserts or chip breakers on positive inserts. So in this row, all of these are chip breakers for positive inserts, and all of these are chip breakers for negative inserts. So from left to right, we go from finishing to, let's say, medium operations to roughing and heavy roughing operations. I think it should be written here so it's completely clear to customer. Each material group has its own reference point. So for steel materials, let's zoom in. For steel materials, the reference point is say low alloyed steel or carbon steel with hardness of say 180 Brinell hardness. Let's say this is our reference point, somewhere in between 180 and 200 Brinell hardness. So then we can say we can follow the conditions written on the box of the insert or in the catalog, and we don't need to calculate anything if we are still in the range of the tube breaker, meaning if we are still inside the values written here. So for example, if we use SF tube breaker here for the reference material for carbon steel with 200 Brinell, and if we still stick inside this area that's highlighted here in green, so for example depth of cut 2.5 millimeters and feed rate 0.16, then we can still apply the values that's in the catalog and or on the box, meaning the cutting is interrupted. There are no problem. The cutting is continuous, not interrupted. There are no troubles with the machine or clamping. It's stable process, and we can run it simply all the time. So if we doing this basic material and we stay inside this field, it's safe to use the basic conditions. On the other hand, if the workpiece material is harder, if it's some high alloy steel or tool steel before hardening, to mention, so up to let's say 45 HRC, then we need to apply this correction factor. It means we need to reduce the cutting speed. Reduce times 0.6, so it means reduce to 60%. On the other hand, if we are doing free machining steels with improved machinability with some extra sulfur content or plumbum content, then we can even increase the base cutting speed even up to 50% higher. That's the basic rule for every material group, and you can find it in this chart also everywhere. In a new catalog, and even before the new catalog, we introduced the WMG, which divide these subgroups into more specific small groups, which gives you more information about the workpiece material, and you can select the workpiece material specifically for each operation. It gives you more correct value for the cutting speed. Right next to it, we have overview of the grades. So first of all, we always display CVD grades. Simply, it's better for continuous cut. For general turning, CVD grades are always better in tool life. Also, we can achieve higher cutting speeds. And then we can see here highlighted by red color these two grades, T9315 and T9325. It tells us that this for this reference material, these are the best choices. Now it only depends on the conditions. So if we have stable cutting, and the best choice would be 9315. If we have some slight interruptions or let's say heavy load, heavy feeding, then it's good to use T9325. We also have here other grades. Let's say in bold, you can see other good choices. And here in normal font, we can see some choices, but not so good choice for steel turning in general. But in some specific cases, it can be better. For example, if we are doing some hard some pre-hardened or hard steel with high abrasion, or some cast steel with high abrasion, then it can be better to use these grades T53 because it has really great abrasion resistance. So it always depends on the workpiece and application. This is the reason why I highlighted before. It's really good to read the notes about the grades, so you will know more details. And when you came across some not so general material, if it's some specific material, then you can select the grade better. Here on the next column we have cemented PVD grades, also highlighted in bold, which are good choices, and always depends on what application. So here material for threading, so of course it will be general good choice for any type of material. And T8330, that's can be a really good choice for interrupted cut in steels. We can basically do interrupted cut by CVD grade also by T9335 if the feed rate is big enough. So if the feed rate is not, let's say, at least 0.15 for this interrupted cut, then this PVD grade will be a better choice. And here we have Pramet grades, which I skipped before, let's say on purpose. Pramet grades are not our main focus, let's say. We focus a lot more into CVD and PVD grades, but we also have these in our assortment for fine finishing of steels. So when we take a look at the overview of chip breakers, we can see chip breakers for negative inserts in the top, and it's sorted in order from let's say the most fine finishing grade to let's say secondary choice to finishing grade, and then some optional choice. And then we have here also Viper inserts. So Viper inserts can be used only for longitudinal turning with no curves, and or for face turning with no curves. That's basically because of the design of the insert. If you're not sure if you can use Viper insert, feel free to ask me, or you can ask your technician. I think they are already aware what Viper insert means, and specific geometry on the insert, which gives you more specific cutting edge. So it's not so easy to calculate the radius if you want to do radius on the workpiece. So it's a very good choice for longitudinal turning. So the first choice for fine finishing, we can see basically FF geometry. It has a very narrow positive T length, only 0.06 millimeters, and very positive rake angle, 22 degrees. So it's the first choice for any fine finishing of steels. And you can see it here on the diagram which area it covers. So only finishing area. Here on a horizontal line, we can see feed rate. So from 0.06 up to 0.2 for FF geometry. And on vertical line, we can see depth of cut, basically from 0.3 up to 0.5. And this area always depends on size of the insert. So of course, FF geometry on very small inserts like CNMG 09 will be smaller. This area will be smaller, and more close to the beginning of the diagram, so it can do smaller feed rates and small depth of cut. Then, for example, CNMG 16, it will be more upper here. So it's always good to check the values on the box of inserts or in the catalog itself. What feed rates is the minimum and what feed rate is the maximum. Is there any question? Okay, so I see there is no question yet. So feel free to is there any question from users SGO?
So they are controlling that one.
So you can analyze with this also. Yeah.
Okay, I hear no questions, so I will mute everyone. Excuse me. Okay, let's continue. So let's continue with the chip breakers. Then we can see here a secondary choice for some semi-finishing. That would be this FM geometry. And you can see directly on the diagram that it's meant for, it's developed for a little bit higher feed rates and higher depth of cut. Again, it always depends on size of the insert. You can find this chip breaker on small inserts. You can find it also on big inserts. So then the diagram with big inserts can move somewhere here. For any chip breaker, it's always needed to check the conditions. What conditions is it designed for? You can see also very nice and detailed sketch of the chip breaker here, which is very useful. In catalog, you can find it also. But I find it here even more clear because you can compare apple to apple on each picture. Then here, right next to the insert, you have some white and black balls, some points, which represents if the insert is the black point represents if the insert or the geometry is resistant to adverse cutting condition, and white means if it's meant for finishing. So basically, FF geometry is meant mostly for finishing, but it can also withstand some adverse condition. And logically, when we go more to the right side, more to the roughing area, of course, our diagrams are moving more to higher feed rates, more to the right, and more to bigger depth of cuts. So upper and more to the right. And here we can see selections for steel, say medium turning. We have here a quite big overlapping of SM geometry, M geometry, and NM geometry. So it always depends what kind of feed rates we want to achieve and also what kind of cutting are we doing. When we take a look at the picture of the cutting edge, it's obvious that SM geometry will be very good for some smooth cutting, continuous cutting, when the chip flow is good and the material doesn't have any inclusions or interruptions in the workpiece. On the other hand, M geometry, because of the negative TLAND here on the cutting edge, it will be a lot stronger geometry for interruptions and for some inclusions in the material, or if the material is hardened only on the surface and then it's tough in the core, then M geometry will be a lot better choice. Of course, we have here another alternative choice. That's NM geometry. That's say very positive geometry, good for soft steels especially, because then the chip flow is very fluent of these sticky and soft steels. Originally, say the primary target of NM geometry is stainless steels, like austenitic stainless steels. But these austenitic stainless steels and soft free machining steels have one thing in common, and that's sticking on the surface of the insert. So this is the case where this positive geometry helps us to avoid the sticking. And vice versa, we can still see the same development in a roughing area. So our diagrams are moving more to the right side and more to bigger depth of cuts. So first choice for roughing of stainless in some continuous cutting, some just a general machining, will be RM geometry with slightly positive TLAND on the tip and with negative TLAND on the cutting on the long cutting edge. And you can see here it's very resistant to adverse conditions, basically because of very wide TLAND here. And our second choice, or let's say even first choice for adverse cutting conditions, or interruptions, for some weld inclusions or some casting inclusions if it's cast steel, then first choice will be R geometry, which you can see again very wide TLAND and additional negative facet and not so positive rake angle. So it's very, very stable and very strong geometry for roughing. Then here OR geometry, it's geometry specific for big size inserts. And again, Viper can be also used for roughing. Especially useful is it's for roughing when you need to achieve a good visual effect on steels. Then Viper, it's really good choice. You can achieve higher productivity, but with still nice visual and nice surface quality. So basically, the same rule applies to also positive chip, insert chip breakers. But the main difference between positive and negative insert is that positive insert have better clearance angle under the insert. So on the flank here on the flank there is bigger clearance angle on positive inserts. So it's always better to use it for fine finishing, especially in stainless steels and super alloys, when the alloy have higher flexibility. So it gives you better surface quality, and it will also give you a better tool life on one cutting edge In comparison, it can be even double in some cases. In super alloys, it can be even more than double for than negative inserts, chip breakers. So don't underestimate positive inserts. It still have a big value because of the clearance angle. So I think I will not waste time right now for overview of all the chip breakers. It's good time for questions. Basically, you can apply the same rules for all the workpiece material groups. And yeah, so now I check your questions if there are any. It's a conversation here. I don't see any questions in the chat. So feel free to ask any questions directly by chat, and also please give me feedback if you want to have some specific training for some specific material groups and more in detail. Next week we will continue in more details for grades. What are, let's say, specific FNG grades? What are specific PVD grades? And we will take a look also more deep into the chip breakers. So how can we recognize from the picture of the chip breaker what is it good for and which actual rake angles are good for what kind of material? We can basically see it already inside these diagrams. And basically for stainless steels, it's better to use more positive geometries than cast iron, for example. For cast iron, it's always better to use, say, perpendicular or inserts with T-length, even for finishing. And of course, aluminum is completely specific case, and non-ferrous materials, because it needs very sharp cutting edge and highly positive rake angle, because without it you have high sticking of the material, even in roughing. For super alloys, it's very similar to stainless steels. You will need sharp cutting edge, but still strong geometry, because super alloys are usually high strength and heat resistant alloys. So we need slightly positive T-length, like SM geometry or NM geometry, and highly positive rake angle, so you can cut the material properly and the chip can slide on the insert. And here in special alloys and stainless steels, it's especially important to remember that positive inserts are a better choice for finishing. In case of not productivity, but tool life and surface quality of one cutting edge. And in hardened steels and hardened cast irons, the rule is very basic: use very strong cutting edge with negative T-lengths, because the high strength of the material will easily break the insert. So you need this kind of protection on the cutting edge. Also here, if you're using like CNMA, so flat insert without chip breaker, it also has rounding, so it's protection against hard hardened alloy steels. There is also written SF geometry here. It's only for a very limited area. So for small depth of cut and small feed rates, SF can be also used in combination with grade T6310 for hardened steels, but for very small chip load. Well, this would be the basic overview. You can apply the same rules for all the materials and all the grades. I think that this this flyer here, it will give you very nice material to have overview all the time with you. So you can download it to your smartphone or laptop, and if you are not sure in the customer what you should use, you can first check what kind of grade, what kind of geometry, and then later search for the insert. Usually it's better to search for something specific that I first will know from here that it will work for the material, then search in the catalog for the right inserts, because you know there are maybe 20,000 inserts and so many combinations that it's a lot easier first to look at the right combination. For example, stainless steel, okay, I need to search for T73 grades if it's continuous cut, okay, T7325, austenitic stainless, and I am doing maybe 0.2 feed rate and depth of cut 3 millimeters. So I'm somewhere here. So I should look for NMR or NM geometry, or even maybe SM. So when I take a look here, NMR should be the first choice. So I take a look into the catalog for the combination of NMR and T7325. And if I find my insert, then okay, I have my first choice, and check the conditions. If I'm in the diagram and the material of the insert match with the material of the workpiece, then I can go ahead. It's always good to check with the technician, let's say check with me if the selection was completely correct, and if it was, then you will have more experience and you will gain experience step by step, and then you can use it even more frequently and do your own selections and be sure that you are doing the right choices. So this would be all for now, for today. On Friday there will be another training for milling selection, where we make overview of milling families. I mean Pramet milling families for indexable. And yeah, I would really recommend you to use especially this file, which can be really helpful. So if there are no questions, I'll check the chat here. Okay, I see no questions from your side. So see you on Friday, and feel free to share the link